Chapter 10. This is chemical bonding, part 2. Last chapter was part 1, this is part 2. More on chemical bonding. Section 1. Section 1, there's not much to say. It's basically comparison with Lewis structure. So Lewis structure, what happens is, and so we're on page about 98 right now in the reader, and in the textbook, we're about on page 399. Okay, Lewis, the problem with Lewis structure is it doesn't explain metals well. You'll notice for the most part, when we do Lewis structures, we try to avoid metals, especially the transition metals. Sometimes we don't, but typically they get a little more messy. The nice thing about Lewis, it's easy to draw, it's relatively fast, but another issue is there's no quantitative results, so we're not going to get numerical values, say for energy or bond length or anything like that from Lewis. So that's another problem. Also, Lewis has trouble with odd electron species. Sometimes you can draw odd electrons with Lewis, but not always. So thus introduces basically this next section. Okay, this chapter we're going to learn some alternate bonding theories besides Lewis. Okay, let me put this up here. Okay, this picture is going to explain to us what the heck a bond is. So I haven't really explained that, but that's what this is for. This is going to be for any sample molecule where the distance between the two atoms is r. So we've got two atoms right here, and the distance is r. This is data specifically for the H2 plus molecule. So r represents the distance between the two atoms. So way out here on the right, this is r axis. They're really far apart, and then as you go closer to the origin, the two atoms are flying closer. On the left-hand scale is energy. Okay, so energy is on that scale on the left-hand side. All right, we're going to use a couple different colors here. First of all, as these two atoms fly closer and closer together, their bonding energy decreases over time, and that's what's represented by this line that I'll outline in blue. Okay. So energy goes down, which is a good thing. Going lower in energy is always stable, and as they fly closer together, the energy goes down and down and down. And this is representing the bonding interaction between the two atoms. That's the bonding interaction. That's because, to use more technical terms, the orbitals are overlapping. And this is, if you remember this term from chapter 7, constructive interference. We're going to have to use that term now. Constructive interference is the bonding action. So they're interfering constructively, which just means their waves are additive. Their wave functions are additive. Now up here, let's get a different color. We'll do this in blue. As they get closer and closer, there's a repulsive interaction represented by this line or curve that I'm drawing out in blue. And that's the repulsion that they have. So the two nuclei, as they get closer and closer, they both have protons or positive charges. When those positive charges get together, they're repulsed by each other. So the nuclei repulsing each other is drawn by this curve here. And this is called the antibond curve. Antibond. Okay? This occurs by destructive interference. Also a term from chapter 7. This means when the wave functions add, they cancel out. When the wave functions add, they cancel out. So the top curve is the repulsive. The bottom curve, the bonding curve, is the attractive curve. Now, when these two add up, literally, mathematically, we add these up, we get this sum curve here at the bottom that I'm outlining in brown. And we call this the sum curve. Literally because we summed up the other two curves. Yeah, that's the sum curve. It's the addition of both the repulsive and the attractive forces of the destructive and the constructive interference. And what happens here, if I get another color, see this dashed line here? Wherever it approaches that horizontal line, this distance right there, that distance right there is the bond energy. That's how we measure the bond energy. The distance from the dashed line down to the bottom part where we call the well. That's the bond energy. That's how we find the bond energy. And this distance from here out again to this bottom well is the bond length. So mathematically we can determine the bond energy and the bond length by wherever that well is. That well is in a perfect place because the sum curve, that's the lowest energy spot. So that means it's the most stable location. And so when these two atoms bond, they're going to bond right here at about 1.6. Okay? Would be about the bond length. That's what a bond is. A bond, there you go. A bond has two parts. That's the key concept for this chapter. It has a bonding part and an anti-bonding part. So every bond is going to have two parts, and we'll see that happen as we go throughout the chapter. It's going to have two parts, the bonding part and the anti-bonding part. When you add them up, you'll get the sum curve, which is going to end up being where it actually makes the bond, the actual bond energy and the actual bond length. So that's what a bond is. In the book, it represents these, it expands this center sum curve, and it only gives you that picture. And you'll see pictures like this, where the sum curve is this one right here. You got the bond energy and you got the bond length at that well position, or the lowest energy position. Okay? But here's, this one's actual data, so that's why I want to show you that one. Yeah?
Why is the bonding and the bond energy negative?
Why is the bonding and the bond energy negative? So that means that if energy is negative, that means energy is released. So it's kind of, as we might say, exothermic, or energy given off. So it totally depends on what the molecule is. It can be kind of anywhere on the y-axis. Okay, but in this case, that means that energy is given off when that bond is formed, overall. Versus having to put energy in to form this particular molecule, the H2+. Okay, that was section 1. Now what's going to happen is we're going to go into section 2. We're going to skip section 2, 3, and 4 until the end of the chapter. We're going to go into section 5, which is going to be page 99 of the reader. Why are we doing this section first? I think it really is more of the basis for the previous section. So we're going to skip section 5 in the textbook. That's page 414. Americans have this weird tradition in December where you go outside, cut a tree down, and then you bring it in your house and you replant it in a pot of water. And so people come up to me all the time on the street. They see me, they say, "Hey, Dr. Topodakis." How can we do that? So I brought my own tree. Okay. This is made out of a copper plate. There's 2. And because I'll put a little more solution in there so it'll be easier to see. Down. There we go. And what you'll see is it's turning black. Trying to submerge it. And without doing much work, I'm going to put some tinsel on it. And so you can see that's actually silver crystals forming on this copper. It's Christmas already right now. And you can see the crystals are growing right for you. The one part that's not growing in the middle is just because it's not submerged. This is a redox reaction where the copper, this was a copper plate, is going from copper to copper 2 plus, and the silver in solution, this is silver nitrate in solution, silver plus, is actually plating onto the copper to make solid silver. So you're actually seeing the silver form right there on it, and that's why it's getting kind of more grayish, obviously silver-like. These crystals will get longer and longer over time. And so I think I'll just leave it in here for a little while. Let's see if I can submerge this part so it really. Yeah, I need a little more to submerge that one part. But what I'll do, if I leave it long enough, and I think I've done it early enough, it's black in the beginning, but then it'll get some more silver. Okay. What I'll do is I'll leave this because the copper, when it comes out, turns blue. So the water, if we leave it, the liquid, it's not water. MO theory, which is molecular orbital theory. Molecular orbital theory. So far, just kind of on the scratch here, you've seen Lewis. Okay. You've seen Vesper. Vesper is actually a bonding type theory that pairs with Lewis, but is its own theory. There's one you're going to see after we finish Lewis, and then there's another one called Valence Bond theory, which is in the book and a little bit in the reader. I don't talk about it very much, but I will mention it when we do our next section, really. So, valence bond is another theory. There's a lot of theories to describe bonding. MO theory is another one. And the reason we like molecular orbital theory is a couple of reasons. It works really well with either paired or unpaired electrons, which Lewis doesn't work as well with unpaired electrons. It can give us numerical results. And it can explain kind of unusual species or chemical species. So it's a really nice theory for us. We're not going to do any of the numerical results in our class, but you will see numerical results if you go on and take more chemistry. So it can have numerical results, but not for us. All right. So let me attempt to explain this. Before I get into it, I have to explain there's two types of bonds that you're going to see in just a moment. A sigma type bond and a pi type bond. Okay? If you're Greek, you're going to love this stuff. Sigma means if you have two nuclei, the bond occurs, when the bond happens between the nuclei, that's called a sigma bond. Okay? A pi bond is a little bit different. Let's say we have the two nuclei here. I'll get a different color. If the bond occurs but does not occur between the nuclei, say above and below the bond, above and below the center line, we call that a pi bond. Okay? So a pi bond occurs not in between the two nuclei, and the sigma bond does occur between the two nuclei. Okay? There's other bonds that go with other Greek letters as well, but these are the only two we'll see in our class. So, how does MO theory work? We need to do a bit of introduction, but it's based on orbitals. And so, for example, SP or F, what kind of orbital is this? S. So let's say we have a 1s orbital here, and it's going to bond with another 1s orbital. Okay? And specifically, we've been calling these orbitals, but to be more specific, they're what we call atomic orbitals, because these orbitals come from atoms. Well, what we're going to do when we make molecules is turn those atomic orbitals into molecular orbitals. Thus, MO theory is the theory of making orbitals that are not atomic, but molecular. Okay? So when we add these up, what happens, the way we would draw it, the way normal people draw it is like this. You just put those two spheres, two s orbitals together, and we now call this a molecular orbital. Now mathematically, I'll show you a different color, we would add these up. Mathematically, it would just be a big blob. But because I cannot trust that I or a TA would understand what the heck this means, you're going to draw two circles next to each other. And that would be two s orbitals now making a molecular orbital. So these are the atomic orbitals here. Then on the right-hand side, I'm going to be drawing the molecular orbitals. Oh, too many I's. There we go. Okay, so we also want, just like the atomic orbitals have names, like 1s, 2s, 2p, 3p, etc., we're going to name our molecular orbitals too. Take a look at this molecular orbital. Here's the nuclei. Can you see that the bond is going to occur between the two nuclei? So thus we'll call this what kind of bond? A sigma bond. Okay? And to remember that this sigma bond came from two 1s orbitals, we're going to put a subscript 1s. Okay? Subscript 1s. By the way, sigma is the Greek letter for what English letter? S. Thus, sigma and S go together. Does that make sense? That's why I assume somebody picked that letter sigma. Okay, now every bond has how many parts? 2. This is called the bonding interaction. The bonding interaction. Let me show you what the 1s orbitals do when you have the other part, which is the anti-bonding interaction. Anti-bonding. That means they're out of phase with each other. And to show they're out of phase, we're going to make one unshaded and the other one shaded. Okay? One's unshaded, the other one's shaded. Or you might say one is a plus and one is a minus, is the terminology that some textbooks use. And so when you add these up, you're going to have a shaded by an unshaded. Okay? What kind of bond is this one? It's still a sigma bond. Because the bond is occurring, even though it's between two different phases, in between the center points. So this is a sigma. They come from 1s orbitals, but to show that this is the anti-bonding, meaning that this is going to have destructive interference, or that the middle, let's get a color here, the middle is going to cancel out. When a shade and an unshade come together, the middle will cancel out to make a void space. So, again, I can't trust to understand if you draw something like this. So we're just going to draw the two spheres next to each other. And to show that it's an anti-bonding interaction, we're going to superscript an asterisk. Okay? So the asterisk is superscripted, and that shows that the second one is anti-bonding, or two different phases together, destructive interference. The top one without an asterisk is the bonding interaction, and that has no asterisks up here. Okay? So it's a bonding interaction, same phase. And if they were both shaded, the same sort of thing. It would be a sigma 1s molecular orbital, or this one is a sigma 1s star molecular orbital. Let's try another one. Those were s orbitals. Let's try p orbitals now. Let's say this is a 2p, and we add that to another 2p. Now, what I kind of didn't really get into in chapter 7 when we did this is the two parts of the 2p are out of phase. So we would say one part, let's say the top is unshaded and the bottom is shaded. They're out of phase with each other. And that becomes really important in this chapter. Now, how to draw the molecular orbital is you just physically put these two together as if they're going to come to fly together to make a bond. And so we're getting, again, the molecular orbital on the right-hand side. Let's redraw these, but draw them next to each other. Draw the shades and the unshades, like that. Now, if you were drawing this kind of mathematically, if you add these two functions, you're going to have a big unshaded blob on top and a big shaded blob on the bottom. But again, that would be too crazy for me to interpret from the drawings. Okay, what kind of bond do you think this one is? Let's call it a pi bond. Pi, because see how the bond happens if I get a different color, above and below the center line. So that's what we call a pi bond. Pi, we subscripted to P because to show that it comes from 2p orbitals. Pi is a Greek letter for what English letter? P. Thus, pi bonds, p orbitals typically form pi molecular orbitals. So p atomic orbitals typically form pi molecular orbitals. Okay, let's try another one. That would be what we call the bonding molecular orbital, or a pi 2p bonding molecular orbital. We could also draw this. Have 2p orbitals that are out of phase with each other. Okay? Remember, every bond has two parts, so I just drew the bonding one. Now I'm going to draw the anti-bonding one. And you just simply move those together and fill in the shades and the unshades. Okay? This would be, can you see again, this is a pi bond, because the bond is happening not along the center line, but above and below the center line. So we call this still a pi. It comes from 2p orbitals, so we still have a subscripted 2p, but because shades and unshades are overlapping, this is the anti-bonding or destructive interference example. So the mathematical representation is kind of tough to draw, and your book has all the mathematicals. Right? Basically, the shades and the unshades cancel out, and they'll just leave kind of this void space in the center with these little pieces on the edges. Let me see if I can show you why. It just looks like craziness. Here's the pi 2p right there. See, it just looks weird. And here's the pi 2p star. Okay. So you can look in your book for kind of artistic renderings, but we're going to draw them as in the first case, the blue cases, where we just draw the atomic orbitals right next to each other. So this is a pi 2p star orbital, molecular orbital. Let's try another one. This will be the last one we're going to try. Sometimes the p orbitals can be oriented different ways, and sometimes you see them oriented this way. This is another 2p orbital, just oriented a little differently. And let's draw this one like this. We're going to take these two orbitals, add them up to make a molecular orbital, which will look something like this. I'm going to draw them just right next to each other, put in the shades and the unshades. Remember, shade and unshade represent different phases that are out of phase with each other. Just like the moon can be out of phase with itself. You can have a full moon, you can have a half moon, you can have essentially no moon. Yeah? Does it matter if the shades alternate or are together, as in these last three cases? If I flip one of them, she's asking, will it matter if I flip one of the p orbitals? Definitely. Yeah, totally. Because in this case, the way I drew it right now, see how the two of the same shade come together. Now, if there are two shaded or two unshaded, it wouldn't matter. If the same shade come together, this is a bonding interaction. Whenever the same shades touch, like up here at the top, and in the other case, same shades touch, that's a bonding interaction. Is this a sigma or a pi bond? This one happens to be a sigma, even though it's coming from a p orbital, because the bond is occurring along the center line. It's a sigma. It comes from a 2p though. It's not a sigma 1s, it's a sigma 2p. And there's no star because it's bonded. So it is possible for a p orbital to make a sigma bond. Okay. Any questions so far? I had to see that before I can draw what's called a molecular orbital diagram. Yeah? How do you know where the shading is in the last case? In the last case, the way I set up the problem, which was this, forced you to fly them in toward each other like this. So the two unshaded parts in this example will touch. So they're always flying together like that. Okay? You'll see when we do actual examples, you'll see how to do the orientation. We haven't done an example yet, so I'm just kind of making up some random possibilities that you'll see later. Okay. Now I know when people first see this, your automatic reaction is to freak out. Okay, I understand that. We're going to start drawing what's called a molecular orbital diagram, which is sort of an analogy to a Lewis structure. But for this kind of bonding theory, at first it looks weird. Just kind of this, like this stuff looks unusual. At first it looks unusual. If you can get over that, these problems are actually extremely easy. You just need to see several of them before you see the pattern. Once you see the pattern, you will be begging us for this kind of final exam question, okay? Because it is that easy. And most students, once they get it, can get full points on it, you know, if you learn it, okay? So if you try not to get freaked out by the weirdness of it, you'll definitely be okay. Okay, how does this work as far as bonding? Well, let's try our simplest example. Let's try to make a hydrogen molecule, H2. Now, how you make this setup is you say, well, H2 comes from two H's. So you're going to do is draw the molecule in the center. And we're kind of getting to page sort of like 101 or so in the reader. And in the textbook, we're somewhere around page 415, 416. Okay, how do you do this diagram? The molecule's in the center and the two individual atoms are on the outside. We're imagining them flying together and making the molecule in the middle. So bonding in the center. Okay? Then what you do is draw the, or write the electron configuration below each atom. So this is a 1s1, and this is a 1s1. Okay, so you got to remember your electron configurations. And then what you do here on the left-hand side is make an energy axis. So a y-axis, just one axis going vertically. And those 1s orbitals will be both at the same energy. So you'd say, okay, there's a 1s orbital on this side and a 1s orbital on this side. And this line here represents the orbital energy level. So we'll say they're approximately the same energy. And I just put them randomly in the middle. They're going to come together to make a bond. Every bond has how many parts? Two, the bonding part and the anti-bonding part. The bonding part is low energy, and the anti-bonding part will be high energy. So you see I have a low and a high energy here for one bond. I beautify it by putting these dots here. That makes, in my eyes, makes it look pretty. Okay? See, the textbook does stuff like this too. It should look pretty much symmetric, but this is a normal thing that I want. And now, a 1s orbital is a sphere. So let me draw the circles just to represent the 1s orbital. When it makes the bonding interaction, that's when they're both the same phase, either both shaded or both unshaded. When it makes the anti-bonding interaction, that means they're both of the opposite phase. Okay? The bonding is always going to be lower energy, the anti-bonding is always going to be higher energy. Okay, let's figure out what these molecular orbitals are called. Is this a sigma or a pi? It's a sigma. It's subscripted 1s, and the top one is a sigma subscripted 1s, but with a star. Again, it's sigma because the bond is happening between the two center points, or along the midline. Just like before, you saw me draw these pictures before, but now it's in the template of what's called a molecular orbital diagram. And now the very last part is to put in the electrons. So let's get a different color for electrons. Both hydrogens are 1s1, meaning they both have one electron. So let's draw one electron in. Notice I'm drawing the spin, both up spin. So I have Total of 2, 1 from each side. That means now for the molecule, what's in the center represents the molecule. What's in the center will now have 2 electrons. So I'm going to fill them up. 1, and now the second one is going to go here because they always want to go to the lowest energy location, 2. And I filled up all my electrons. There's my 2 electrons. This is a molecular orbital diagram. Both electrons are in the bonding orbital. There's no electrons in the anti-bonding upper orbital. Okay, they're both in the bonding orbital. From this, there's 2 common questions that we'll ask you. One is about magnetism. If you remember back to chapter 8, I know a long, long time ago, is this para or diamagnetic? This is what's called diamagnetic. How do you know that? You look in the center, you look here, in the center, and because you're looking at the molecule, and you see that, oh, there's only paired electrons. Paired electrons means diamagnetic. If there was some unpaired electrons, we'd call it paramagnetic. Diamagnetic means essentially there's no magnetic ability or no magnetic moment. Okay, so basically let's say H2 is not magnetic. There's another thing that we commonly calculate from this, and that's called the bond order. From the last chapter, the bond order can be calculated. It's the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital divided by 2. Okay? So, let's go to the new page. Bond order in this example, the number of electrons in the bonding molecular orbital, that's the sigma 1s, the one without the star, is 2. 2 electrons in the bonding molecular orbital. Minus, we have 0 electrons in the anti-bonding molecular orbital, the one with the star, the sigma 1s star. So minus 0, divided by the number 2, because there's 2 electrons per bond. And this will give a bond order of 1. What does that mean? This is a single bond. Okay, it's forming a single bond. So if we go back up here, according to Lewis, we would draw this like this. Okay, that would be the Lewis structure, forming a single bond. Or, in our new language, bond order is 1. The 2 in the denominator she's asking, is that always there? Yes. That's a constant. That never changes. That's because there's 2 electrons per 1 bond. So you got to divide by 2 to change the bonds. Okay. Let's try another one. So if I ask you what's the molecular orbital diagram, you draw this. If I ask you what's the magnetism, you say diamagnetic. If I ask you about the bond order, you'd say it's 1. Let's try another one. Let's form the molecule helium-2 plus. Now because this will be an odd electron species, we can't draw this using a Lewis structure. How do we draw the molecular orbital diagram for this? Well, helium-2 plus comes from 2 helium atoms flying together to bond. Now if it was 2 neutral helium atoms, then when they flew together to bond, you'd have helium-2. But to get the plus charge in there, one of them has to be charged positively. So just like before, we have a y-axis of energy. Let's draw the write out the electron configuration. It's 1s2 and 1s1. This helium plus only has 1 electron. And there at some random given energy in the middle. This is the 1s orbital for each. Every bond has 2 parts, a bonding low energy and an anti-bonding high energy. We beautify it with dots or dashes here to kind of show where these lines come from. Yeah? And we remember that a 1s orbital is a sphere, or we draw it as a circle. So when it's bonding, these two spheres come together in the same shade, whether both shaded or both unshaded. And when it's anti-bonding, they're the opposite shade. So far, you should be noticing that this diagram looks identical to the previous. Okay, so far, this is what I would call a template. The template looks identical. The bottom one is a sigma 1s bonding, and the top one is a sigma 1s star. Sigma again because the bond happens between the center points. The 1s because they come from 1s orbitals. And the star on the top because they're opposite shades of destructive interference. Now let's put in the electrons. On the left it's 1s2, or a neutral helium, so 2 electrons. From the atom on the right, this atomic orbital has 1 electron, it's 1s1, helium plus. So now we have 2 on the left, 1 electron on the right, for a total of 3 electrons for the molecule now. The molecule's electrons go in the center. So I'm going to go 1. The second one wants to be at low energy, it'll be the opposing spin. And then the third one, this is now full, so the third one has to go up here to the anti-bonding orbital. So now I only have 1 electron in the anti-bonding orbital. That is the molecular orbital diagram. By the way, all these orbital pictures here, the circles, on the final, you won't have to draw those. Okay? I'm just showing you where things come from. So why is the bottom one the way it is? Why is the top one the way it is? On the final, these circles, or the molecular and atomic orbitals, you won't have to draw. You will have to be able to label the energy level. Okay. Is this para or diamagnetic? Yeah, if you look at the center, there's 1 unpaired electron at the top, so we call this paramagnetic. The bond order, let's do the bond order now. It's the number of electrons in bonding molecular orbitals, that's 2. Minus the number of electrons in anti-bonding molecular orbitals, that's 1 in the starred orbital. Divided by the number 2, or 1/2. 1/2 means it's kind of like a half of a bond. Is this bond length relatively long or relatively short? Relatively long. Is it relatively high energy or relatively low energy? Low energy relatively. Good. By the way, what would it mean if I had a helium neutral here, or I was forming helium-2? If I was forming helium-2 and had 1 more electron here, can you see that I would have a 4th electron up here? What would be the bond order in that example? 0. That means essentially it doesn't bond, or would not exist. And we don't know anything really naturally, at least, about helium-2. Okay, that's how you do everything that involves s orbitals. Next time, we'll start into the p orbital. Shopping.